Okay, so we're now going to talk about convex set systems. And the basic idea is that as we progress further, we're going to start looking at trying to approximate, um, it's like data, if you will. It's like by looking at balls around points and then looking at the intersections to represent their connectivity. Okay, so this falls into this general setting. It's like a convex set systems, which we'll talk about. Okay. So, um, so in particular, we're going to look at sets of common points, sets with common points. Sorry. Okay, so sets with common points. So, um, so in particular, we're going to start to think about under what circumstances, if you have a bunch of sets and pairwise, it's like they have intersections, whether there's some non-trivial joint intersection of all the sets. Okay, so we consider circumstances in which pairwise intersections of convex sets imply that the intersection of all the convex sets is non-trivial. Okay, and of course the motivation for doing this is sort of fairly clear. Um, it's like obviously pairwise intersections are easier to check than if you can conclude something from pairwise intersections to saying that the intersection of all the convex sets is non-empty. It's like that would of course be helpful to know. And so one of the results, it's like, which is in this vein, is called Helly's theorem. Okay, and it says the following. Let's say that you have F, which is a finite collection of closed convex sets in d-dimensional space. It's a finite collection of closed convex sets in Rd. Okay, and so then the claim is that every d plus 1 of these sets have a non-trivial intersection if they all have a non-trivial pairwise intersection. Okay. Okay. So so I'm not going to prove this. It's like, but let me just sort of remark that the way you go about uh, setting up the proof is by induction on D, which is the dimension, it's like, of the containing space. So as an example, it's like when D is equal to 1, you just have the real line, and you just have to show that every two of these sets have non-trivial intersection if they all have non-trivial pairwise intersections, which is of course trivial because you've already said every pair has a non-trivial intersection. So if D is equal to 1, right, every two of these also obviously have a non-trivial intersection just by the assumption, if you will. Okay, and then it's like you induct a second dimension to prove this. Okay, so I'm not really going to go too much into the details. But again, the idea, if you will, is that you do this by induction. It's like on the dimension. Okay, and the details are in the textbook if you're interested. Okay, but let me sort of make a few remarks about this. All right, and in particular, the obvious question is, well, can we relax the conditions that these sets are closed and convex? Okay, so you can't relax the closedness condition, but you can relax the convex condition. And in particular, if you think about it, one of the, it's like if you imagine things like balls or anything, one of the properties, if you will, it's like which is true of convex sets is that when you intersect them, the intersections have some nice properties. Okay, and so that's basically what's going to happen. It's like when you relax the convexity assumption on each of the sets, is that you replace that with a condition on properties of the intersection. It's like between these sets. So let me just state the remark. So the remark is that the convexity assumption in Halley's theorem can be relaxed. Right. So this sort of the result holds if all the sets are closed and there's some property about the pairwise intersections. Okay. The pairwise intersections have to be contractible. So I'll say more precisely what that means, but I mean intuitively, it's like what that means is that you can take that intersection and you can somehow smoothly deform it to a point. Okay, and we'll see it's like what that means more precisely in a little bit. Okay, so let me just stop here for a minute.